Let us look at proposition number 113 of book 10 of Euclid's Elements. The proposition says the square on a rational straight line, if applied to an apotome, produces as breadth the binomial straight line, the terms of which are commensurable with the terms of the apotome and in the same ratio, and further the binomial so arising has the same order as the apotome. So let's see. Let A be a rational straight line. Let BD be an apotome. What the proposition is saying is that if we apply the square on A to BD, we get a breadth KH, a binomial, and the terms of the binomial, that is KF and HF, are commensurable with BC and CD of an apotome, and they are in the same ratio, and KH has the same order as BD. So let's see how we can start from here and arrive at here. Okay, construct KH such that BD by KH is equal to the square on A. So A square is applied to BD, producing as breadth KH. Let CD be the NX to BD. So which means BC and CD are rational and commensurable in square only. Now construct G such that BC by G is equal to A square. Now, since A square is rational, because A is rational, A square is rational, BC by G is also rational, which implies G is rational. Therefore, G is rational and commensurable in length with BC. Now, BC by G is equal to BD by KH because both are equal to A square, which implies BC is to BD is equal to KH is to G. Now, since BC is greater than BD, because of this proportionality, KH is also greater than G. Now, construct KE equal to G. So, KE is also commensurable in length with BC because G is rational and commensurable in length with BC, and K equal to G. So, K is also commensurable in length with BC. So, we can write this proportion as BC is to BD is equal to KH is to KE since KE equal to G. In conversion, so BC is to BD. So when we do the conversion, we are looking at the remainder. So BC is to BD, CD is equal to KH is to HE. Now we find F such that KH is to HE is equal to HF is to FE. Now the remainders have the proportion KF is to HF is equal to KH is to HE. What does this mean? KH minus HF is what? KH minus HF is KF. So KF. HE minus FE. HE minus FE is HF. So KF is to HF is also equal to KH is to HE, which means KF is to HF is equal to BC is to CD. Why? Because KH is to HE is also equal to BC is to CD. So we can say KF is to HF is equal to BC is to CD. That means KF and HF are commensurable in square only because BC and CD are commensurable in square only. Now, KF is to HF is equal to HF is to FE. KF is to FE is equal to KF square is to HF square. So here we have KF is to HF equal to HF is to FE. So HF is the mean proportional. So if we say KF is to FE, remember this means KF, HF and FE are in continued proportion. So KF is to FE would be the square of the ratio of KF is to HF. So kf square is to hf square, which means kf is commensurable in length with fe, because kf square is commensurable with hf square, because kf is commensurable with hf. That means kf is commensurable in length with fe. Kf is commensurable in length with ke. Why? Because kf is commensurable with fe. That means that the other part will also be commensurable with the whole. So kf is commensurable with ke as well. Since ke is rational and commensurable in length with bc, that means kf is also commensurable in length with bc, because kf is commensurable with ke. So we have seen bc is to cd is equal to kf is to hf. Alternately, we can write it as bc is to kf is equal to cd is to hf. That means hf is commensurable in length with cd, because kf is commensurable with bc. So bc is to kf equal to cd is to hf, which means cd and hf are also commensurable in length. So kf and hf are rational straight lines commensurable in square only. So kf plus hf equal to kh is a binomial. So now let's see. If bc square is greater than cd square by the square commensurable in length with bc. See, it could be either commensurable or incommensurable. So let's say commensurable in length with bc. Then because of this proportionality, kf square is also greater than hf square by the square commensurable in length with kf. And if bc is commensurable with a rational straight line set out, so is kf. If cd is commensurable with a rational straight line set out, so is hf. And if bc and cd are incommensurable with a rational straight line set out, so are kf and hf. These three statements are based on this proportion. Now let's look at the other case. If BC square is greater than CD square by the square incommensurable with BC, then KF square is also greater than HF square by the square incommensurable with KF. And if BC is commensurable with a rational straight line set out, so is KF. If CD is commensurable with a rational straight line set out, so is HF. And if BC and CD are incommensurable with the rational straight line set out, so are KF and HF. So therefore, we have arrived at these conclusions. KH is a binomial. The terms of KH, that is KF and HF, are commensurable with BC and CD of an apotome, and they are in the same ratio. And KH has the same order as BD. That is proposition number 113 of book 10 of Euclid's Elements. Again, let me remind you, there is a link to a PDF book which describes all these propositions in detail. Please feel free to download it, refer to it, and if you think somebody else can also benefit from it, please do share. That's it for now. Bye.